So now we will consider how EmDrive complies with the second basic law of physics, which is the conservation of energy. If you look at the diagram, you can see that the input energy is a form of microwave energy. This is then stored in the cavity with a time constant, which we refer to as the cavity time constant. And the stored energy is equal to Q times the energy lost per cycle. Now, the energy lost per cycle is constant because the input energy is constant and the frequency is constant for a simple case. With an accelerating cavity, then some of the stored energy is going to be transferred into kinetic energy, which depends on the thrust and the mass of the vehicle that is being accelerated. But most of the energy input to the cavity is actually lost as thermal energy. So if we're suggesting that the stored energy decreases because some of it is transferred to kinetic energy, because the energy lost per cycle is constant, it must mean that the stored energy, as the stored energy goes down, the Q goes down. And we've already seen that, that the thrust of an EmDrive cavity depends on the Q of the cavity. And therefore, we have a mechanism which shows that as you accelerate a cavity, so energy is transferred to kinetic energy, which causes the thrust to decrease. We have basically a mechanism to show that EmDrive complies with the conservation of energy. But this also means that if you are designing a mission, you really have to take this into account. Therefore, the thrust and the mass and the power all have to take into account that the conservation of energy, the law of the conservation of energy, must be complied with. So we've said that the cavity has a time constant, and now we'll look at how we calculate that time constant. So first of all, we need to look at a plot shown on the left of the slide of the power inside the cavity as you sweep across the frequency range. Now that the power in this case is the telemetry value of the power, the output of the power detector, and so this is measured in volts, and in fact this is a resonance plot for a flight cavity. So you can see as you move across the frequency range, as you approach the resonance frequency of the flight cavity, which is 3,851 megahertz, the power inside the cavity reaches a peak. And this peak, the value of this peak, depends on the Q of the cavity. And we can define the Q of the cavity as 2 pi times the energy stored over the energy lost per cycle. And you can measure the Q from this actual resonance plot. If you take the half power point on the power telemetry, then measure the frequencies at these two half power points, the upper and lower half power point, then what's called the 3 dB bandwidth is the difference between these two frequencies. Now, once you've determined the resonant frequency and the 3 dB bandwidth, you can actually have a measure. This actually gives you a measure of the Q of the cavity. Now, the time constant, which is what we're looking for, is actually the time taken for the cavity to either store or to release the microwave energy, the microwave stored energy. And it is very simply defined as the time constant equals 1 over the 3 dB bandwidth. I think it's helpful to look at analogies when we're considering a microwave cavity. And as with analogies, as with most analogies of electrical concepts, we fall back on water. And in this case, we look at the level of water inside a bathtub. Now, if we assume that the bathtub, that the cavity is not moving, it's fixed in one place, we can simply think of the bathtub having a constant input flow of water, and the energy and the level of water in the bathtub, which represents the level of stored energy, will simply go up until it reaches a level, energy level 1, where the height of the water level causes the losses through the drain plug, through the drain in the bathtub. These losses will equal the input flow of water. So we have a simple static situation where the losses equal the input. The bathtub is not moving, so there's no other losses. And in fact, this is equivalent to an EmDrive cavity being fixed in position, perhaps to measure static thrust. And we have a maximum Q of the cavity. The energy level 1 is a maximum level, and therefore the thrust is a maximum. So now we'll look at a second bathtub analogy. And in this case, the bathtub has a second drain hole leading to a tank, which represents the kinetic energy that is being transferred from an EmDrive cavity to the vehicle that it is accelerating. Now, in this case, because you have two energy losses, one the thermal losses and the second the kinetic energy losses, then the water height that is necessary to achieve a constant water level will be lower than it was before, where you only had a single drain hole in the bathtub. And this is simply equivalent to the kinetic energy being transferred to the vehicle that you're accelerating, and therefore the thrust decreases because the stored energy is decreasing, just as the stored energy level in the bathtub is reduced to the stored energy level 2. Now, the thing to remember with an accelerating vehicle is that as the vehicle speeds up, there will be an inertial load on the vehicle itself, and this actually limits the rate of increase of the loss of kinetic energy. We will look at this in more detail later. We'll now look at an analogy of a particularly interesting situation. This is where we have the microwave cavity, the EmDrive thruster, being started under no load conditions. And in this analogy, we've shown the no load as being a very large additional drain hole at the bottom of the bathtub. And in this case, the no load output is so big that you can never raise the stored energy level in the bathtub more than just a slight covering over the bottom of the bathtub itself. In other words, the stored energy 3 is very close to zero, because as soon as you start putting water in at the input, it immediately drains away at the output. This is an analogy of an EmDrive thruster which is totally free to move. It has no initial load, it's not accelerating, so it has no inertial load. And in the case of a microwave cavity, immediately after switch on, the stored energy follows an exponential rise, whereas the increase in kinetic energy follows a square law. And you very quickly get to a crossover of these characteristics, which is equivalent to the very low stored energy level in the bathtub, with the water simply just flowing over the bottom of the bathtub and straight out of the no load output. This is actually a very real situation, which we shall look at next. We'll now go from the simple analogy to a real-world example, and for this I've chosen a 20 kilogram CubeSat, which is about to be propelled by a 3.85 gigahertz EmDrive thruster operating with an input microwave power of 40 watts. And the plot shows the output of a simple mathematical model of this situation, which plots kinetic and stored energies together with thrust for the first 25 microseconds after switch on of the thruster. Now, to actually enable this model to run, we put an initial load of 1 microgram into the system. And what you can see from the graph is that the dashed blue line representing the kinetic energy goes up as a square law. The red dotted line, which is the stored energy, goes up as an exponential rise, and the thrust is shown as the red line. And you can see at 20 microseconds after switch on, the rise in kinetic energy actually equals the stored energy, which is at this point tapering off to basically a fixed level. The thrust itself it simply shows a peak at about 8 microseconds, and then it drops off rapidly until the crossover point is met, when it's very close to zero. Therefore, what we're suggesting is that if you have a satellite in orbit, absolutely no loads on it at all, you simply cannot start up the acceleration of the satellite without the introduction of a preload. How you actually do this, we will cover in the next slide. There's a number of solutions to this, but it's also important to recognize that if you're actually going to measure thrust on a test rig, you also need to apply a preload. And we saw that in the first slide, where we discussed the demonstrator engine being rotated on an air bearing, a rotary air bearing, and the rotary air bearing itself had a frictional torque component which acted as a preload on the thruster and enabled us to watch the demonstrator engine start to accelerate on its rotary test rig. In this slide, we show the results of the mathematical model for increasing levels of preload. So this again is the CubeSat thruster. And we show that if you increase the preload to 2 micrograms, we really get very little improvement in the situation. What we actually get is a slightly higher peak of thrust, but certainly by the time you reach 20 microseconds, you're back down to 0 in terms of thrust. So that's the black dotted line. The green dashed line shows that things are improving. As you go up to 10 micrograms, it gets better at 50 micrograms, but it is still eventually tailing off and will reach 0. You only actually reach a constant level of thrust if you apply 500 micrograms, which is equivalent to 5 micronewtons of preload to this CubeSat thruster. So you need 500 micrograms of preload, and how can you get it? Well, there are a number of ways. Simply using the AOCS momentum wheel, that's the momentum wheel that's used in the attitude and orbit control system of any satellite. You can use that to provide a preload as long as the thruster is positioned along the Z-axis of the satellite and it has a significant separation from the satellite center of mass. So simply switching on or increasing the speed of a momentum wheel for a very short period of time will give you a preload on the thruster. Alternatively, you can actually rotate the satellite so that the Z-axis of the satellite is aligned with the Earth's gravity vector, and you can apply what's effectively gravity loading on the thruster, and again you need this 500 micrograms of loading. But probably the best way of doing this, which avoids having to use the AOCS system at all, is to actually attach a small solenoid which is aligned along the thrust axis, and in this case for the CubeSat, a 10 millisecond pulse of 2 watts applied to a solenoid will provide the required 500 microgram load. So you apply it for 10 milliseconds, but long before you actually get to the end of the solenoid pulse, in fact after 35 microseconds, the inertial load of the accelerating spacecraft will apply a load to the thruster, and this will ensure continuous thrust. What is interesting is that the first example of this happening, we believe, was way back in about 2008, when a Russian satellite called Nubilini, again a small satellite, small science satellite, was testing something like an EmDrive thruster in orbit, and they got results which they were not able to say were absolutely successful. None of us understood at the time, I don't think, that you needed to preload a thruster to achieve actual acceleration of a satellite. So now we look at another energy loss mechanism in an EmDrive cavity, which is due to the Doppler shift which you get in a very high Q superconducting cavity. If you look at the diagram, you can see that we're accelerating in the correct direction. That is large end to small end going to the left. And if you look at the velocity of the cavity itself, you can see that the velocity at the small end, the increase in velocity is less than the increase in velocity at the large end, which is after the wave has been reflected from the small end to the large end. And you've simply got an increase in cavity velocity because the cavity itself is accelerating. And it's this actual difference in cavity velocities at each reflection that causes an overall Doppler shift in the wave itself. If indeed the velocities of the guide were the same at each end, then you would get Doppler shifts which cancelled each other out. So in a symmetrical cavity, you don't see this Doppler shift, this overall Doppler shift, if you accelerate a cavity. If you did, there'd be one or two instruments on aircraft that wouldn't work. But because of the increased cavity velocity and the different guide velocities at each end of the cavity, then you will get an overall Doppler shift. And this can be calculated, and there's a mathematical model for the Doppler shift which we did, and the results of that are shown in the plot on the right of the slide. Now here we're plotting the actual Doppler shift in hertz of a 4 gigahertz cavity with a Q of 5 by 10 to the 7. So this is what we call second generation superconducting cavity. And you can see that for a positive acceleration, which is the red line, as the number of transits of the electromagnetic wave up and down the cavity increases, so the actual Doppler shift increases, but in a negative way. So the frequency goes down, basically. So if you're accelerating the cavity, the frequency goes down, and thus you are therefore introducing an energy loss because you're simply decreasing the frequency of the electromagnetic wave. And this is the thruster operating in what we term its motor mode. If you actually use the thruster to decelerate a vehicle, so we have a negative acceleration, this actually gives a frequency increase. The model will just simply show a frequency increase due to the Doppler shift. And this represents, in fact, an energy increase in the thruster, and therefore illustrates the thruster operating in a generator mode. it's just like any electrical machine, really. You can use them as either motors or generators. So it once again it indicates that an EmDrive thruster is simply an electrical machine. Combination of a very high Q cavity and a significant acceleration actually causes a catastrophic loss of thrust due to the Doppler shift. Effectively, the frequency of the travelling wave is lowered so much that it moves outside the bandwidth of the cavity. So we clearly need to correct for this, and we can do this by extending the axial length of the cavity and also lowering the input frequency. So effectively we are trying to match the cavity to the Doppler shifted frequency, and we are lowering that input frequency also to match this Doppler shift. Clearly, this can't be a continuous process. If it was, then we'd end up with an infinite cavity length and a zero input frequency. So what we do it over a short pulse. In the case of what we term third generation cavities, we actually use a pulse length about the same time period as the time constant of the cavity itself. We extend the cavity axial length using piezoelectric elements and a small sliding wall section at the small end of the cavity. Piezoelectric elements are commonly used in high energy physics accelerator cavities. This is the ones that have a cavity extension simply because of the very high forces that are applied to both ends of the symmetrical cavity. And the length is compensated for by using piezoelectric elements. Now we use it to not only extend the length of the cavity to match the lowering frequency due to the Doppler shift, but we also decrease the input frequency throughout the pulse so that it matches this Doppler shift. In practice, for EmDrive engines using high Q cavities, which require significant acceleration, we actually use two cavities, and the power is switched between cavities. So when the power is switched off for the first cavity and the cavity is allowed to reset, the power is being applied to a second cavity. Well, what this means is that the microwave system associated with these cavities can operate in effectively continuous wave mode, which is the more efficient way to operate these pieces of equipment. If we look at the plot shown on the left of the slide, this shows the difference between a compensated thruster, so-called third generation compensated thruster, shown in the red line, and the blue dotted line, which shows an uncompensated thruster. And you can see that by the time you reach 20 meters per second, which is 2g acceleration, the uncompensated thruster simply loses virtually all its thrust, whereas the compensated thruster is improved quite dramatically in that it loses about half its thrust under maximum acceleration, but this is still a usable third generation thruster. To look at the Doppler correction in a little more detail, we'll assume a two-cavity engine with cavity time constants of nominally 1 second. In this situation, we would apply a power pulse of 1 second to the first cavity, and this is shown as the full line in the plot. First plot to the left of the slide. Now, because the time constant of the cavity is a nominal 1 second, the actual Doppler shift will carry on over a 2 second period, and the frequency correction and the extension of the cavity length will also be applied over almost 2 seconds. You can see that just before the end of the 2 second period, the extension reverts back to its original axial length, and the Doppler shift drops back to 0. So if we look at the two cavities, and this is shown in the right-hand plot, you can see that for cavity number 1, which is the dotted line, from switch on, the thrust and the stored energy increases exponentially till it reaches a maximum at the end of the nominal time constant of the cavity. At this point, the power is switched off, and the dotted line then drops exponentially to approximately 0 once you reach the second time constant period, which reaches 2 seconds. Now, meanwhile, if we go back to the first 1 second period, the second cavity is decreasing, and that's shown by the dashed lines. It starts to power up again after 1 second when the power pulse is switched to the second cavity, and reaches a maximum thrust after 2 seconds. So if you add the two thrust characteristics of the two cavities together, you can see that it's effectively a continuous output with small dips during the switch of input power between the two cavities. Now, rather conveniently, you can compensate for kinetic energy loss by using pulse modulation. So if we look at the kinetic energy gained by any vehicle in an acceleration period termed delta KE, you can see that is equal to the mass of the vehicle divided by 2 times the square of the increased velocity. That's v2 squared, which is the terminal velocity squared, minus v1 squared, which is the initial velocity over this time period. The mechanical energy that you're putting into the vehicle during this period, EM, is equal to force times distance, which is the definition of energy after all. And this is the force times the average velocity VA times the time period T. If you extend that, you get it equal to K PT. That's K is the specific thrust, P is the power, and T is the time period, times the average velocity, which is V1 plus V2 over 2. In a resonant microwave cavity, the stored energy is ES, and it's given by Q times the EL, which is the electrical loss per cycle. This actually extends to Q times P, the power, divided by F0, the resonant frequency. So if we take these equations, we can define the system efficiency for an accelerating vehicle. And the efficiency is going to be the output energy, which is delta KE, divided by the input energy, which is the mechanical energy EM, plus the stored energy ES. And if we do a performance analysis of a heavy launch vehicle, and we'll do this for the very maximum velocity of 100 kilometers per second, this shows that as the pulse length decreases from a maximum of 4 microseconds, the thrust and acceleration, that's the red line and the black dotted line, increase significantly, whereas the efficiency, which is the blue dotted line, a dashed line, decreases. It's again an example of conservation of energy, which almost must be used in mission planning. So we will use the performance analysis of a heavy launch vehicle to look at the variation of pulse length as the vehicle velocity increases. We've said that from the equation for the mechanical energy input, that this will clearly increase with the absolute value of the vehicle velocity. Okay, the faster the vehicle is moving, the more delta KE will increase, causing a loss of stored energy and loss of thrust, unless you do something to maintain efficiency. And what you actually do is to decrease the pulse length to maintain the optimum efficiency as the velocity of the vehicle increases. If we look at the plot shown on the left-hand side of the slide, this is illustrated by performing a performance calculation for the heavy launch vehicle at a constant acceleration of 1g. And you can see that to maintain the 1g acceleration and the optimum efficiency for this vehicle, the pulse length needs to drop down from about 800 microseconds when you're running at a very small velocity of 0.1 kilometers a second. It drops down to well below 1 microsecond by the time you reach 100 kilometers per second. So we'll try and illustrate what we've been talking about with pulsed input by reverting back to our bathtub analogy. And here we have the kinetic energy which is being stored in the vehicle as the vehicle accelerates. This is illustrated by a series of small tanks underneath the drain hole from the bathtub, which represents the kinetic energy transfer from the bathtub, which is the thruster, to the vehicle itself. So as the vehicle velocity increases, the rate of kinetic energy loss also increases. In other words, if you like, the hole in the bottom of the tank gets bigger, and the water flow increases. If we are going to keep the kinetic energy in each of the storage tanks at the same level, we must therefore decrease the length of the pulse of the water coming into the tank. So simply we just decrease the time period of this water inflow as the vehicle accelerates and the rate of outflow from the hole at the bottom of the tank increases. It's just a simple illustration of how we compensate for kinetic energy loss in an accelerating cavity.